Welcome to Beyond the Comfort Zone Talking Shit with KING-KAMBUF. You know, if you've ever had to deal with those really, really tough decisions, the ones that are right at that intersection of pure design, hard economics, and what the city will actually let you build, then you already know.
You know that it's just so much more complex than just sketching something that looks good.
Exactly. And today, we are diving deep. This is a massive knowledge transfer we're about to do.
Yeah, we're dissecting the core logic from this DBSK daily lecture and assignment from the ARC 503 studio. We're talking about the mid-rise mixed-use urban block. This is our shortcut for you.
Shortcut from what, though?
From just preliminary massing, the blocky shapes, to the incredibly detailed, absolutely essential systems coordination that has to happen.
That title is a mouthful. Let me just get it out there. DBSK Daily Lecture and Assignment, Monday, December 1st, 2025, 9:08 a.m. PT topic.
Okay.
Studio V Mid-Rise, Mixed-to-Use, Urban Block Massing, Circulation Logic, and Early Systems Coordination.
Right. It tells you this is not late reading.
No, but this is fundamental stuff. I mean, the mid-rise mixed-use block, that's the absolute backbone of, modern, walkable, human-scaled cities. It's the building type that really defines street life.
The stakes are just enormous because at this scale, maybe 6, 8 stories, it's the tightest crucible you can imagine.
It's where everything comes together.
Everything. Design, structure, fire and life safety, urban policy, financing, the public good, they all have to converge. And honestly, they often violently conflict.
And if you get that logic wrong at the beginning,
the whole project will fail. It'll either collapse financially or it will just fail functionally. It won't work.
So our mission today is really to pull out those high leverage decisions from this studio module. We're trying to get past the what if we made it curvy phase of design.
Yeah, and get right into the brutally honest, how does this actually have to be built and what on earth is it going to cost phase?
We're pulling out the logic that lets a design actually survive.
Huh.
Survive scrutiny from code officials, performance targets, community review boards, all of it.
And to start, we have to stabilize the baseline. We have to be on the same page. We're talking about the standard urban block cross-section. You have to picture this rigid hierarchy in your mind.
Okay, lay it out.
The bottom 1 or 2 stories, that's the podium. This is for active public uses, retail, lobbies, resident amenities, that kind of thing.
Right, that's the engine. That's what drives the street life. It's the part the city actually sees and touches.
Exactly. And then stacked right on top of that podium, you get your 4 to 6 stories of residential units or maybe office space.
And that's all driven by efficiency.
100%. It's about maximizing leasable area, getting high visibility at grade for the retail. But, and this is the architect's constant daily challenge, you have to balance that powerful economic engine with real civic responsibility.
Meaning things like daylight, safety.
Daylight, safety, building genuinely engaging streets. That tension right there was where all the risk lives.
Okay, let's start unpacking that. So we have the basic stack, active uses on the bottom, density that you can lease or sell on top. But before we get all excited about, sculpting a cool facade or designing the perfect apartment, we hit a wall.
You hit the invisible fence.
Invisible fence. I like that. So the architectural form is just immediately and severely restricted by government rules.
Huh.
What is the single most powerful tool that sets those boundaries right from day one?
That invisible fence is, it's dictated by the International Building Code, the IBC. Specifically, you've got to look at Chapter 5. It's all about heights and areas.
Okay.
This chapter is the hard constraint. It dictates the absolute maximum limits of your design's footprint and its volume before you've even drawn a single detailed floor plan.
So Chapter 5 doesn't care if your building is beautiful or has great views.
Not at all.
It's just defining a hard physical safety stop on size, and it's all based on risk tolerance.
Yeah.
So what are the 3 key metrics it restricts?
Okay, so it dictates the maximum number of stories you can stack up.
Okay, number of floors.
Then, the maximum overall building height measured in feet.
Got it.
And this is the really critical one, the maximum total floor area. And that includes both the aggregate area of the whole building and the area that's permitted on each story.
And all 3 of those limits depend on what?
They depend completely on the building's function. In our case, it's mixed use, which complicates things, and the proposed construction type, which is categorized from type I, the most fire-resistant, all the way down to type V, which is the least.
I always see the code as a sort of menu of trade-offs. The sources really emphasize that you can earn extensions to these limits. So how do we buy ourselves more size, more height?
You're right, it is a trade-off. The main ways to get those extensions involve active fire protection. So putting automatic sprinkler systems throughout the entire structure.
That's a big one.
A huge one. And upgrading your construction type to something heavier, more resistant. But for this mid-rise typology we're talking about, the key strategic move, the one everyone uses, is the podium separation.
Ah, the podium opportunity. Let me challenge you on this, though. Is it really an opportunity, or is it more of a financially risky compromise that demands absolute discipline? Sounds like we're just layering on complexity to get around a height limit.
It is absolutely a compromise, but it's a compromise that's driven by economics and the demand for density. This podium technique is essential for getting vertical flexibility.
So how does it work exactly?
We build those bottom 1 or 2 floors, which, often have parking, loading docks, big retail spaces, using really robust, high fire resistance, Type I concrete construction.
The heavy stuff.
The heaviest. This Type I podium then acts as a kind of heavy fire shield, and it allows us to stack a lighter and cheaper construction type on top of it. Something like a Type 3 wood frame or maybe Type 4 mass timber.
Now, that sounds almost like you're cheating the code. How is that legally justified? How do you stack 2 different buildings on top of each other like that?
It's not cheating. It's all codified. It's right there in IBC 510.2. It's known as the podium building, or a Type IAIA separation. The code requires a really specific, really rigorous separation between that lower heavy podium and the upper lighter stack.
And that separation is what?
It's enforced by a 3-hour fire separation slab. The code, it essentially treats the building above that slab as a structurally and legally separate building that just happens to be sitting on a very, very robust fireproof base.
Okay, tell us more about that 3-hour slab.
Oh.
What makes it so different and so expensive beyond just the fire rating?
Well, the 3-hour rating requires density. It requires material depth. So it's typically a thick, heavily reinforced concrete slab. We could be talking a 10, maybe 12 inches deep.
Wow.
And sometimes it has special fire-rated materials or, intumescent coatings, depending on the loads and what the fire expectations are. This is where that cost trigger lives. The sheer volume of concrete, the increased complexity of coordinating all the MEP systems, the plumbing, the electrical, the vents that have to pass through this critical barrier, and the longer curing time for this massive piece of structure, it all just increases the front-loaded capital expenditure, the CapEx, and it extends the construction schedule.
So it's a necessary complexity,
Yeah.
but it's what you have to do to unlock the height you need to make the project financially viable.
Precisely. It's the cost of entry for this building type.
Okay, so once we've maxed out the volume using this podium trick, we almost always see the structure start to step back. You called it controlled erosion. Is this just an architect trying to be artistic, or is this forced on us by zoning?
It's almost always forced. It's primarily driven by zoning ordinances that regulate the relationship between your building and its neighbors, often through things called bulk requirements or setback requirements.
So this controlled erosion is entirely for civic purposes.
Entirely. We pull the massing back to reduce those deep canyon-like shadows that get cast onto the street or onto the adjacent properties.
Okay, so you're protecting your neighbors.
You're protecting your neighbors' access to light and air, and often it has a benefit for your building too. You create these usable, safe social terraces for your own residents on the upper levels.
So the step back is really the moment the building acknowledges it has a responsibility to the public realm, to the city around it.
That's a perfect way to put it. If we didn't do this, we would just create these hostile, shadowed environments at the street level. We have to sacrifice some of that upper level floor area, which, let's be honest, means less sellable space, to improve the quality of the city outside our property line.
Let's get into the specific forms. The source material talks about 3 major massing families that are used to assess viability on a city block: the U-shape, the liner bar, and the courtyard block. How do we quickly analyze the trade-offs that come with each one?
This choice of form is the first huge design commitment. It drives everything that comes after: structural decisions, light, amenities, everything.
Okay, so let's start with the U-shape. What's its core strength? Why would you pick that one?
The U-shape is the champion of light and air, no question. Because it's open on one side, usually facing the street or maybe a park or a good view, it just maximizes the intake of natural light and ventilation, and it gets it deep into the building plan.
And you get that space in the middle.
Exactly. It naturally provides this excellent semi-private courtyard space in the center, which becomes a highly desirable amenity for residents. It can be a quiet refuge from the street.
Okay. And the liner bar. That one just seems like the most structurally efficient a big rectangle.
It is. It's the most straightforward, the least structurally demanding. It's just a long, narrow rectangle that creates a really strong, consistent street wall.
Okay.
So it maximizes the amount of active storefront facing the sidewalk.
And the structure is just simple.
Super simple. It's repetitive, often standardized bays. The circulation is simple, usually just a single corridor with cores at either end. But while it's highly efficient in terms of area, its big weakness is shadow casting. If you orient it east-west, it can create these very long, deep shadows all day long. And it offers much less internal amenity space than the other forms.
Which brings us to the most traditional urban form, the full courtyard block.
Right, the full courtyard block. This creates a completely protected internal space. It can be a serene oasis, totally shielded from the noise of the city. However, and this is a big however, this form presents the critical challenge of managing what we call deep plan zones.
And what are those?
If the residential perimeter, the part of the building with the apartments, is too deep from the window to the corridor, you run into severe daylight penetration issues, especially for the units that face into that inner courtyard and especially on the lower levels.
And this ties directly back to our risk register from the source material.
It does. This is risk number 5, inadequate daylight. This is exactly why comparing these 3 forms based on light equity, on how fairly they distribute light to all the units, is essential right now at the very beginning of the project.
So, to sum up this first section, we established the non-negotiable size constraints from IBC Chapter 5. And that forces us to evaluate the form based on these trade-offs between cost, complexity, and that immediate civic duty to provide light and air.
That's the foundation. Get that wrong, and nothing else matters.
Okay, so we've established the static volume, the overall shape. Now we have to talk about dynamic movement. Circulation. How do people, delivery trucks, maintenance staff, and most importantly, emergency services, how do they all travel through this complex building?
Right. And these core decisions are absolutely paramount. They dictate not only your life safety compliance, but also, pretty brutally, the economic performance of every single floor plate.
Yeah, because the core is space you can't lease.
Exactly. The core decisions define what we call non-leasable area, so minimizing its footprint while maximizing its efficiency is everything. And the fundamental safety requirement for a building this height is what we call the 2-stair imperative.
Why are 2 separate stairs mandatory? It seems like a lot of space to give up.
It's the bedrock of egress fundamentals under IBC Chapter 10. For a mid-rise residential building, redundancy is completely non-negotiable. In the event of a fire or some other emergency, if one of your exit paths is compromised, say it's blocked by smoke or flames, the other one has to be safely and remotely accessible.
And remote is the key word there. I understand the code is very specific on this. You can't just put the 2 stairs right next to each other in the same area.
That's a classic rookie mistake that just kills a design instantly. The code mandates a minimum separation. The stairs have to be separated by a distance that is greater than or equal to 1/3 of the diagonal measurement of the area they serve.
1/3 of the diagonal.
1/3. That rule is designed to ensure that if something happens at one end of the floor, the path to the other exit is still viable, it's still clear. This critical fraction, the 1/3 diagonal, it immediately dictates how long your corridor has to be, and it forces the architect to pull the cores apart.
Which can have a huge impact on how you lay out your apartments.
A dramatic impact on unit layout efficiency. That one single rule instantly increases your corridor square footage, which is overhead that you can't sell.
And speaking of inefficient paths, what's the one circulation feature that the source material says we absolutely must minimize?
Dead-end corridors. We classify these as design dead.
Design dead. I like that.
They have to be kept severely short to meet the IBC Chapter 10 limits. Often it's only 20 feet in a building with sprinklers. A dead-end corridor forces an occupant to travel down it, realize they're blocked, and then have to backtrack to find the correct exit.
Which is a terrible proposition in an emergency.
A highly risky one. The longer the dead end, the higher the risk, and the more likely your design will just get rejected in plan review.
So the efficiency challenge is making sure that the travel distance, that's the path from the farthest apartment door all the way to the exit stair, meets the code limits. What are those typically?
Usually around 200 feet in a fully sprinkled residential building. If your building footprint is too vast, or if your core placement is off, you run into a huge problem.
What's the immediate consequence?
You fail the travel distance test. And the only solution at that point is adding a 3rd core, a 3rd stair.
And that's a project killer.
It can be. That 3rd core eats up, I don't know, 400 to 500 square feet of floor area on every single floor, space that you can no longer monetize. That is often enough to just decimate the project's economic viability. Gone.
So the core is obviously much more than just the stairs. It's the central service hub. We group the elevators, the stairs, all the vertical shafts into these life safety clusters. What are the pros and cons of the two main strategies for how you group them?
We generally look at centralized versus offset cores. A centralized core is often very efficient for circulation.
How so?
It minimizes travel distance, it minimizes the overall corridor length. You can serve the most area with the least amount of circulation space. However, structurally, placing a massive, stiff element like a concrete, shear-walled core right in the middle of your building plan can create problems.
What kind of problem?
If the rest of the building mass isn't perfectly symmetrical around it, you risk something called structural torsion when it's subjected to seismic loads or heavy wind.
Structural torsion sounds both expensive and terrifying. So what about the other strategy, the offset core?
An offset core, placing the core more toward one edge or a corner, can be great for unit planning. It allows for cleaner, deeper units along the main facade, which can maximize views or light.
But there's a trade-off.
Always. The trade-off is often longer corridors to make sure that your remote secondary exit still meets that 1/3 diagonal requirement. So you gain some planning flexibility, but you potentially increase your structural complexity and the overall footprint that you're dedicating to just circulation.
And a bad core decision, as the source lecture notes, creates awkward apartments, wastes leasable area, and just guarantees headaches with the code officials down the line.
It's a domino effect.
Let's talk for a minute about best practice versus just minimum compliance. The sources hint that a master architect goes beyond what the code strictly requires. What are some of these advanced safety components that speak to a more resilient building?
That's really the difference between designing for mere legality and designing for a real-world catastrophe. We're talking about enhanced refuge components.
Like what?
For instance, incorporating areas of refuge for residents with mobility impairments. These are safe, 2-hour, fire-rated waiting areas, usually inside the stair enclosures. They often have dedicated communication systems where people can safely wait for first responders to come and help them.
And what role does smoke play in this more advanced thinking? Because we always hear that smoke is the real killer.
It is. Smoke is the primary killer in building fires. So advanced designs will incorporate strategies like smoke compartments and pressurization systems that aren't always strictly required in every mid-rise jurisdiction, but they massively increase safety.
How does a smoke compartment work?
It limits the spread of smoke horizontally across a floor plate. It basically creates fire-rated walls and doors that contain the smoke to one area, which provides clear travel paths to both of your remote exits. Designing these elements in from the start, it shows you're committed to public safety, you're anticipating real-world crises, and you're minimizing liability.
So, to wrap up circulation, the core placement is the single most important decision for egress compliance, which directly informs how much money you can make, your net rentable area. Every foot of wasted corridor is $1 lost.
Absolutely. And having locked down how people move, we have to anchor the building physically. The structural logic is the highest leverage decision after that initial massing. It's the skeleton that determines cost, schedule, and all of your internal planning efficiency.
Right. I saw the top 10 line items for CapEx. Structure is often number 2, right after the cost of the land.
It is. If you mess this up, the project is dead.
So we have to harmonize the grid. Why is the choice of the structural bay size so critical for a mixed-use building? What dictates that ideal span?
The grid has to serve two masters. It has to serve the wide, flexible spaces you need for retail and parking in the podium, and the narrow, repetitive constraints of the residential units that are stacked above.
Two completely different needs.
Totally different. For the podium level, we're targeting standard bays of about 25 to 30 feet. That span is really efficient for reinforced concrete. It minimizes your column count while keeping your slab thicknesses acceptable, and it gives retail tenants the flexibility they demand.
But, and this is the big but, those wider bays have to translate cleanly to the smaller residential modules above. That's where the real integration challenge is.
That is the integration challenge. The column lines must align perfectly with standard residential unit depths, which usually range somewhere between 28 and 32 feet. The goal is, it's a kind of geometric genius.
What do you mean?
You're trying to design the grid so that every single column and every structural beam can hide cleanly inside an internal party wall. That's the wall separating two apartments, or maybe inside a corridor wall. If that structure protrudes into the habitable space, you lose usable area, you complicate all your interior finishes, and you just confuse the occupants.
So the ultimate goal is finding a common denominator for the grid that works for the big retail spans and the narrow apartment modules without your column count just exploding. What happens if you fail to harmonize the grid?
You introduce what's called a heroic transfer, and this is the single biggest early structural risk you can have.
Let's stop right there. The term heroic transfer sounds exciting, but in construction economics, all I hear is massive cost overruns. Describe what that looks like and why it's such a future risk.
A transfer is when a column coming down from the residential floors above does not stack cleanly onto a column below it. It's misaligned. So you're forced to use a huge, deep girder to catch that load and then move it laterally to the nearest column or foundation point.
And how big is huge?
A transfer girder can be 3 or 4 feet deep, sometimes more.
And what's the immediate consequence of that massive depth?
It eats your ceiling height. It concentrates an immense load onto a single point, which dramatically increases the complexity and the size of the connection itself. It also complicates seismic design because this element becomes a critical fuse for how loads get distributed. The moment you introduce a transfer, you increase your steel tonnage, your concrete volume, the complexity of the detailing.
Which all translates into massive cost and constructability risk.
Every single time. This directly addresses risk number 2 on our list, misaligned grid units. You have to solve this on day 1.
Okay, moving to lateral resistance. The building needs to resist wind and seismic forces. Referencing the ASCE 722 standard, how do we choose between stiffness and flexibility in our resistance system?
We really rely on 2 primary tools, shear walls and moment frames. We're designing for resilience here.
Okay, explain shear walls.
Shear walls are the simplest and most cost-effective way to get stiffness. They are thick, reinforced concrete walls, and they function basically like a stiff cardboard tube, preventing the building from racking, from moving side to side.
And you put them where?
You naturally align them with elements that are already stiff. The elevator and stair cores and utility shafts, they are incredibly efficient for lateral load resistance.
And moment frames.
Moment frames give you more planning flexibility because they don't require continuous walls. They rely solely on the strength of the connection between the column and the beam to resist those bending forces.
So they're harder to build.
Much harder. They're structurally more nuanced, far more complex to detail, and significantly more expensive. For a typical mid-rise building, we almost always use a hybrid solution. We rely on the core shear walls for the bulk of the primary lateral stiffness, and then we supplement that with some perimeter moment frames or rigid beam connections to make sure the entire building acts as one cohesive structure.
So the most critical rule for project viability, the source material just hammers home again and again, is the absolute necessity of clean column stacking.
It is the golden rule. Columns must stack cleanly from the foundation all the way to the roof. Every single heroic transfer is a cost trigger, a schedule threat, and an unnecessary complication. The job of the architect in this early stage is to find that unified grid that avoids these transfers. Lock down the structure early to prevent a catastrophic cost blow-up later on.
Okay, the skeleton is up, the movement paths are clear. But without the building's essential nervous system, the vertical services, the MEP, this building is just an empty shell. These are the elements that are so often overlooked but allow the structure to actually function.
And they eat up permanent, valuable vertical space.
They really do.
You're right. This is where coordination chaos begins if the architect hasn't asserted control early. The vertical surfaces or shafts are the unseen arteries of the building, and they demand dedicated, contiguous, stacked space that passes through every single slab.
So what's on the essential vertical MEP checklist that demands this precious vertical real estate?
The list is long and it's demanding. You need plumbing stacks for waste and fresh water, which require dedicated, sound-insulated wet walls to hide them.
Okay.
You need trash chutes and recycling paths, high-voltage electrical risers and telecom cables, the large ventilation ducts for delivering outdoor air, especially with modern high-performance systems, and the distribution paths for heating and cooling, whether that's pipes for a central system or refrigerant lines for individual heat pumps.
That is a staggering amount of vertical infrastructure. And I could see how if you just let the engineers scatter these elements based on whatever's convenient for a local unit, the coordination just goes haywire.
Precisely. That is exactly why we implement the efficiency of what we call the shaft spine concept. The architect has to commit very early to clustering the majority of these vertical services into a cohesive, centralized spine.
And what are the critical benefits of locking this shaft spine down early, beyond just simple organization?
There are two massive benefits. First is predictability. When your structural grid, your core, and your shaft spine are locked in place, you have stabilized the critical 20% of your plan that drives 80% of your downstream certainty.
You reduce the chaos.
You reduce the coordination chaos and you allow the other disciplines to design around fixed constraints. Second, maintenance. Clustering simplifies long-term maintenance, repairs, and upgrades, which saves a massive amount of operating expenditure down the line.
So where is the optimal location for this critical spine?
It's usually immediately adjacent to the primary core. Often it's nestled right against the elevator shaft or a stair enclosure. Or it's carefully aligned along a major internal party wall. This strategic placement ensures that the unit wet walls, the kitchens and bathrooms where the most demanding plumbing is, can connect horizontally to that main stack with the shortest, most efficient runs possible.
And this solves one of our key risks.
This directly addresses risk number 3, shaft conflicts, which requires us to lock these preliminary verticals right now.
Let's talk about the intersection of these systems and energy performance. You have to reference IEC 2021 C403. This code forces us to consider complex modern equipment like DOAS. First, what is DOAS and why does it require such large shafts?
DOAS stands for Dedicated Outdoor Air Systems. It's an essential tool for energy efficiency in modern buildings. Instead of forcing occupants to open their windows for fresh air, which wastes a massive amount of heating and cooling energy, DOAS brings in a 100% fresh air centrally, conditions it, and then distributes it to the unit.
And it recovers energy in the process.
Crucially, yes, it often incorporates energy recovery ventilators, ERVs, or heat recovery ventilators, HRVs. These capture energy from the outgoing stale air and use it to pre-treat the incoming fresh air.
So it's a heat exchanger that saves energy. A big one.
Exactly. But moving air requires significantly larger ducts than moving liquid, like plumbing. These ducts are substantial, and if you don't appropriately size the chase, the dedicated space for those vertical ducts early on, you will end up with a devastating conflict when the mechanical drawings finally arrive.
And what does that conflict look like?
You might find a major air duct running smack through a primary structural beam, which means expensive, major rework for everyone.
So we're not just providing space for pipes and wires anymore. We're sizing the space based on the dictates of modern, large-scale, energy-efficient requirements like these huge air delivery systems.
You have to. If you don't, you're designing a building that can't be built.
Okay, so we've created this efficient, compliant machine. Now for the final and maybe the most important question, how does this machine meet the street? How does it contribute positively to the public realm?
Right, and this requires the architect to transcend the role of just being a designer and step into the role of the architect-builder-statesman.
That role requires balancing the private need for profit with the public need for a thriving, safe city. Let's start with the street wall. Why does its design single-handedly dictate the entire pedestrian experience?
The street wall is the face of the building. It's the visual and tactile boundary between private and public. It determines whether the sidewalk feels protected and safe or if it feels hostile. A successful street wall has to maintain a sort of enclosure and comfort. If it's set too far back or it's too high, it creates this uncomfortable, exposed environment.
And what about transparency at the ground level? It seems like that's a non-negotiable component of a healthy urban interface.
It is absolutely non-negotiable for active uses. Transparency requires extensive use of glass, visibility for retail spaces, lobbies, ground floor amenities. The source is explicitly warned against the cardinal sin of urban design,
Which is?
the creation of long blank walls.
Describe that feeling of walking past a long blank wall and why it's so hostile to the urban experience.
It's actively detrimental to the city. A long blank wall, long stretch of concrete, a parking garage entrance, blank utility wall, it creates a dead zone. It completely eliminates eyes on the street, which dramatically reduces perceived safety.
It feels dangerous.
It feels dangerous. It reflects sound harshly, which increases noise pollution. It provides zero visual interest, so pedestrians just rush past it. It interrupts the continuity of retail activity. It is the very definition of a hostile, unsafe, and boring urban interface.
So what we need are active edges and well-designed thresholds. What are the elements that create that difference between a welcoming interface and a dead one?
It's about the frequency and quality of interaction. Active edges require frequent entries and storefronts. They provide visual stimulation and points of human interaction. They need overhead elements, canopies, awnings, shading structures to protect pedestrians from the rain and sun.
And lighting.
The lighting has to be safe and warm, not blinding or stark. The core narrative check is crucial here. You have to ask yourself, will this block feel alive and safe at 10 a.m. on a Tuesday and at 8 p.m. on a Friday? If that edge dies after business hours, you have failed the urban test.
And we also have to look beyond our own building line and manage the curb zone. We often forget that design has to extend into public infrastructure.
Indeed. The curb zone is a highly constrained piece of real estate where public and private needs just collide. The architect statesman has to advocate for the right mix of uses there. You have to account for drop-offs, designated rideshare staging areas, loading zones for the retail,
And bike lanes, transit stops.
and increasingly dedicated, protected bike lanes and accessible transit stops. Yes.
And the decision to prioritize those curb uses is, in a way, a political act disguised as a design choice. For example, sacrificing a few parking spaces for a protected bike lane or a dedicated bus stop.
It is. It's prioritizing sustainable public mobility and safety over private vehicle storage. And that's a choice that has to be made transparently. Furthermore, we have to integrate what the source calls microclimate infrastructure,
Meaning trees.
meaning trees. Trees are not decorative flourishes. They provide essential shade, which dramatically lowers the microclimate temperature for pedestrians. They manage stormwater runoff. They provide psychological comfort. Their placement has to be carefully coordinated with all the underground utilities and the building entries.
Let's address the ethical requirement. The assignment rubric weights ethics and community at 15%. When we're stacking all these residential units, what is the core ethical concern that the architect has to mitigate?
The core ethical concern is ensuring light equity. It's about avoiding the creation of light-poor units. In the pursuit of maximum density, it's very easy to design units that only get minimal, borrowed daylight, or are stuck facing into deep, dark internal courts. The mandate is that units must be equitable in light access.
But there's an inevitable trade-off between maximizing the number of units and guaranteeing enough lights for everyone. How does an architect defend that trade-off?
Transparency is the only way. You have to document the trade-offs. If a deeper plan is required for structural efficiency, then the architect has to ensure that things like light shelves or higher ceilings or the strategic placement of windows are used to mitigate that loss of light. Creating units that are technically legal but are psychologically deficient is an ethical failure. We have to design for human health and comfort, not just the bare minimum of the code.
And what about the human flow at the ground level, beyond just the retail?
The ground floor has to be socially inclusive. Is the lobby accessible and welcoming to all members of the community? Are the retail offerings integrated well? And critically, are the back-of-house utility flows, the trash management, maintenance access, loading docks, are they humane and safe? You can't just create dangerous or visually blight-ridden service zones just to make the front facade look good.
Okay, we have layered constraint upon constraint. We have code, movement, structure, systems, urban fit. In a high-stakes project environment, how do you track all these variables at the same time? It seems like you have to move from qualitative design goals to hard, quantitative performance targets.
Absolutely. Beyond simple code compliance, we manage what are called non-code performance targets. These are measurable numerical metrics that define a high-quality, high-value building.
What are the key performance targets we have to set during this early massing phase that will lock in the future performance of the building?
Energy use intensity, or EUI, is paramount. EUI measures the annual energy consumed per square foot, usually quantified in kb2 per square foot per year. We have to set a very ambitious target early on.
Like what?
Often aiming for an EUI goal of, say, less than or equal to 28 to 32 kiloBTU per square foot per year, which is well below what standard code requires. That early target forces every single structural and systems decision that follows.
I want to focus on daylight again. We talked about avoiding light-poor units. How do we quantify what sufficient light actually is?
We use metrics like SDA 30000's 50%. This stands for spatial daylight autonomy.
Okay, break that down.
The goal is often set high. At least 50% of the resident spaces should receive sufficient daylight, which is defined as 300 lux for at least 50% of the occupied hours of the year. If your massing scheme creates really deep plans or is heavily shadowed by neighboring buildings, you will immediately fail this measurable target. And that's a signal that the design has to change.
And the facade, the most expensive element after the structure, that requires specific numerical placeholders for performance too, right? What are the two major numbers we lock in for the envelope?
We lock in U values and solar heat gain coefficients, or SHGC. The U value measures how quickly heat escapes through a wall or a window. We target low U values for efficiency, a U wall between 0.045 and 0.06. For windows, a U window between 0.28 and 0.32.
And the SHGC, why is that number so critical, especially on the east and west exposures of the building?
SHGC measures how much solar radiation, how much heat passes through the glass. If you let too much heat in, your cooling loads explode, and that kills your EUI target. The sun is weakest and highest on the south side, but it's lowest and most intense blasting right into the facade on the east and west.
So you have to block it.
You have to. Therefore, we require the lowest SHGC targets on the east and west facades. We're aiming for something like 0.22 to 0.30 to block that intense solar heat gain and prevent catastrophic overheating and high cooling costs.
Let's finally confront the money. This all translates into dollars. The source material provides a mini pro forma snapshot. Where do our early architectural decisions have the most catastrophic financial impact?
The impact is heavily concentrated in the big three cost drivers. If we look at the top 10 line items, you see structure as line item 2, facade envelope as line item 3, and MEP systems as line item 4. They're where all the money goes, right after the cost of the land itself.
But a minor change in one of those.
A minor change, like adding one heroic transfer or failing to right-size a DBSK chase, can ripple through the entire budget and sink the project.
Give us the hard numbers from that snapshot so the listener really understands the scale we're talking about.
The total estimated CapEx, the cost to build the physical structure, is approximated at around $296 per square foot of gross area. When you realize that the structure alone accounts for roughly $44 a square foot and the facade is close to $53 a square foot of that total, you understand why simplifying the massing and standardizing the structure isn't just good practice, it's a survival mechanism.
And what about the long-term costs?
The estimated OPEX, the operating cost, is projected at $9.25 per square foot per year. Efficient design cuts both your initial construction costs and decades of operational expenditure.
So to bring this all home, let's revisit that risk register. What are the 5 key risks that the studio assignment demands be resolved immediately in this early phase before you're allowed to move on to detailed design?
These are the 5 showstoppers, the things that will kill a project if you don't address them today. First, over-complex massing. Avoid unnecessary cantilevers or volumetric shifts that challenge that unified structural grid. Simplify early.
Second.
Misaligned grid and units. Resolve this today. Columns must align perfectly with party walls. Failure means transfer girders and massive cost.
Third.
Shaft conflicts. Lock your preliminary verticals now. Commit to the shaft spine layout and make sure the chases are sized for modern systems like DOAS.
Fourth.
Overheight FAR issue. This is just basic zoning verification. If your proposed massing exceeds the floor area ratio, the FAR, or the height limits, the project is dead on arrival.
And the 6th.
Inadequate daylight. This is the ethical check.
Yep.
You have to compare your massing forms, the U shape, the line or bar, the courtyard early on, to assess light equity and ensure you are meeting your SDA targets for human health.
So the core lesson here, what we've extracted from this ARC 503 module, is that these early stage decisions just carry asymmetrical weight.
They absolutely do. The initial commitment to the structural grid, the specific core location, and the precise shaft spine layout, those 3 things dictate the code compliance, the cost, and the long-term performance for the entire future of the project.
So the leader, the architect, builder, statesman, as you call them, has to provide clarity in what the lecture calls the fog of possibility. You have to lock down the few critical constraints immediately.
Lock down the height based on that I-type 3 separation. Lock the 28 to 30-foot grid. Lock the egress paths and lock the shaft spine. This stability is what protects the project from debilitating rework and catastrophic cost increases later on.
And protects your ethical standing.
And as we emphasized, ethical leadership requires complete transparency. You have to state your assumptions, you have to reveal your design blind spots, and you have to document your logic so that the community and any future reviewers can fully follow your reasoning on the trade-offs you were forced to make.
That brings us right back to the final ethical challenge, weighted at 15% of the rubric. We've established core function. We've established compliance with all the structural and life safety codes. But what single priority decision, the one related to urban fit, not just code, what decision has to be locked down today to ensure this building actually meets its civic duty?
It is the street wall alignment priority. The decision has to be to irrevocably Maintain active frontage. You must commit to transparency and activity at the ground level. If you compromise that essential transparency, if you allow a parking garage entrance to dominate the sidewalk, or if you create long blank walls just to save a few dollars on glazing,
And you failed.
you have created a building that is structurally and numerically perfect, but which actively damages the city's safety and its vibrancy. That is the final test of good integrated leadership in this kind of development.
A perfect structure that results in a hostile urban environment is, by definition, a failure. Thank you for joining us on this incredibly detailed and structured exploration of integrated architectural design.
My pleasure.
We hope you feel much more informed about the high-stakes connections between design, systems, and city life. Keep mapping those connections, and we'll catch you next time on Beyond the Comfort Zone.